Thank you so much to Steffi and to Marcel and to Hubert and to Yossi for the extraordinary, as J.G. Ballard always said, urgent junction making, which DLD does. And I'm very excited to welcome you all for these last two sessions today, welcoming Dimitar Sasselov and also Yoko Ono. We're going to have two different conversations, and we will start with a short speech by Dimitar, followed by a Q&A. Dimitar Sasselov is not the first time at DLD. He was introduced actually through the one and only John Brockman and Edge.org. And John, 2 years ago at DLD, said, "It's urgent that you meet Dimitar." Many things have happened since then. We have connected Dimitar to artists all over the world, and artists admire Dimitar's work. A particularly fascinating thing is that actually many artists, before they decide to become artists in their teens, think that they want to go into astronomy. There seems to be a pattern there. When we did at the Serpentine the show with Wolfgang Tillmans, which Julia Peyton-Johns and I had organized, Wolfgang told us the story that as a teenager he was about to become an astronomer, and he and Dimitar had the most extraordinary encounter. Dimitar explores stars and planets at Harvard University, where he is professor of astronomy. His research has to do with the discovery of many different planets. He's the founding director of the Harvard Origins of Life initiative, a cross-disciplinary research effort bridging the physical and also life sciences. He has just published this extraordinary book, which is called The Life of Super Earth: How the Hunt for Alien Worlds and Artificial Cells Will Revolutionize Life on Our Planet. And in this book, Dimitar actually shows us something he told me whenever we met, that biology is the future of astronomy, something which is so intriguing. He explains why this expanded notion of astronomy includes biology, geology, chemistry, and is actually a very exciting search for new planets, for new worlds, for new life. Dimitar Sasselov is one of the great public intellectuals of the 21st century. He inspires artists, architects, philosophers, and many others. A very warm welcome to Dimitar Sasselov.
Thank you, Hans, you're very kind. Good evening. Now that the sun has set, I can tell you I love the sunrise, especially at dawn and a few minutes after the sun has already come up. But there is a problem. I don't like getting up early in the morning. So the way I solve that problem is becoming an astronomer. So I work at night, looking at the stars until the sun rises, and then I go to bed. But there was one day 8 years ago when I did get up early in the morning, really desperately early in the morning, and that was June the 8th, 2004. And the reason I did that, because it was the transit of Venus. Venus, once in a century and a half, passes between us and the Earth, and we can see its dark silhouette projecting on the shiny surface of the star that we call our sun. I don't know if you can see it on the right-hand side there. That's Venus, early in the morning, as seen from Boston. And it was a very mystical experience. Here in Europe, Wolfgang Tillmans, the great photographer and artist, captured it in a more stark terms, just like we astronomers like to see it. But what I saw was this mystical dawn experience between the clouds. And so why was it so important, and how does this relate to today, 2012? What is special about 2012? Well, it's not the Mayan calendar. It is the year of the planetary transits. Why? Because first, and very importantly, Venus is transiting again, the last time this century, the last time for our generation. Next time will be in 126 years. And second, there is a space telescope named after Johannes Kepler, which is using this same technique, transits, in order to discover planets. And we think this year, 2012, is when it's going to discover a planet just like the Earth out there in a very distant star, for the first time ever. So it is a moment which is very special in our time, and especially in science, which I tried to capture in this book for you that Hans was so kind to tell you about. It is the convergence of two game-changing developments in science. And these are the two things I want to tell you about tonight and to discuss. One of them is in astronomy, the other one is in biology. And this book is first and foremost about super-Earths, which is a new type of planets, which we have only been able to discover for the first time recently. Most of them recently were discovered by this same space telescope I already mentioned, the Kepler telescope. And they're a new type of planet because although they have properties similar to our own Earth, they're slightly bigger, and there is no such planet in our solar system. But what we discover is that planets like that are plentiful around other planetary systems. So there are very many super-Earths out there. And when we look at them back, we are trying to put in this big picture our own planet Earth. First of all, it is a whole continuum. It is super-Earths and planets like the Earth. In fact, it was just last month that our Kepler team, for the first time, managed to discover planets the size of the Earth, which you see there. Venus and Earth are just in between them. One of them is slightly smaller than Venus. The other one, Kepler F, is almost precisely the size of Earth. So these are orbiting the same star. That's why they are both called Kepler 20. I'm sorry to say, but we don't have very poetic names for our planets. We expect to find thousands of them. And so we'll run out of names very quickly, as in next month. So we just call them by numbers, Kepler 20, Kepler 10, Kepler 9. You see that. If you have a better idea, see me after the talk. In the meantime, what we now know about Earth, discovering these super-Earths, is that Earth is simply a member of the family. Mind you, a smaller one, maybe even marginal member of the family, but still a member of the big family of super-Earths. So Earth is one of those super-Earths. So this has really resulted as an effort which was done by many people, most recently by the large team of the Kepler telescope, named after Johannes Kepler, that you already heard about, for good reason. He was the first to predict the transits of Venus, which were very important a few centuries ago. The telescope is in space. It uses transits to discover those planets. I am very privileged to be part of the original team, which is running it. And we are discovering planets by the buckload, several thousand of them already as candidates. The most important results which can be reported at this stage in the third year of its mission is that, number one, super-Earths appear to be very plentiful, and they often come in systems of several around the same star. And the second thing, which we've learned, is that they're very diverse. That is, our solar system and the planets in our solar system, as diverse as they appear, are not the whole story. And this is, of course, great because it gives us an opportunity to reassess the potential for life on other planets and how many such potential habitats are out there in our galaxy alone. So the estimate is really a staggering number. But our galaxy is a big galaxy too. So 100 million of them is not necessarily that big. It just means that we have a fighting chance to find something interesting, maybe even signatures of life in our lifetime, around a nearby star with a planet of that sort. And that is also a historic shift, really a historic shift in the human universal frame of reference. That Earth, our planet Earth, is one of a multitude of Earths. This is very similar to what happened about 500 years ago, when Earth was suddenly a planet out of just 6 at the time. Now we see that this is a phenomenon which is all across the universe, a very important shift in our frame of reference, and one that brings us to the next question. So then, what about life? Is there life on other planets? If there are planets like the Earth, what about life? And I have to say here that although we talk about life all the time, we actually do not have a scientific definition for life. We don't understand its basic nature. We still believe we can look for it because we at least know that it's a chemical property of ordinary matter. And as we heard in an amazing talk this afternoon by Lisa Randall, we know quite a bit about ordinary matter and the way it bonds in complex chemical ways. So if life is, in a sense, at least in my definition here, equivalent to chemistry, or biochemistry, as we would say, then we have some clues of how to look for it. And you will ask me, well, how do you look for something which you don't even understand? And more importantly, how do you look for something which you cannot visit? The answer is remotely. Remote sensing of atmosphere gases is a technique which we fortunately have learned very well over the past century. We can apply it even to most distant stars at the edge of the universe. So the same way in which you would expect gases produced by life forms here on Earth to accumulate in the atmosphere and to be visible from many hundreds of light years away by somebody looking at Earth and noticing that something is unusual about the large amount of oxygen gas in our atmosphere, we hope we can do the same in our search away and beyond Earth. And then it is the obvious question that we cannot assume that life on other planets, life elsewhere, will have the same basic chemistry. And that obvious realization has brought the second game-changing scientific concept that I want to share with you tonight. It has brought the field of chemical synthetic biology, the possibilities for alternative biochemistries, life or biochemistries which are radically different from the one which all life on Earth is based on. And that, in itself, in my humble opinion, is the dawn of a new revolution in science and technology. The combination of those tools of synthetic biology, which allow us to supplement what we have now as the synthetic tools of organic chemistry. So allow me to have just one slide, which is technical, because I want to convey to you this new development which is starting and which may transform life on our planet. When we talk about chemical synthetic biology, we think of a field in science which has as its major object of study the concept of a minimal cell, or quite often it's called the artificial minimal cell. This is a chemical entity which has the functions, the basic functions of life chemically, without necessarily being a self-sustaining living organism. And there are two approaches in which you can understand and maybe even build a minimal cell like this. One is a top-down approach, the other is a bottom-up approach. The top-down approach is the one in which you take existing life, the simplest and smallest organisms that we know of here on Earth, and you try to reduce it to the basic functions, to its basic genome, which would still make it function like a living thing. That has been an effort which has gone on now for 50 years or more, and although it has some great breakthroughs, like the ones which are mentioned here, it has essentially failed to complete the goal of creating a minimal cell. So what we've recently in our team and others have turned to in the last few years is the bottom-up approach, where instead you try to build those functionalities which we associate with life from the bottom up, from chemistry, from building up the basic molecules, and creating an entity which behaves like a living entity. The exciting possibilities here, if this if this really succeeds as an effort, the exciting possibilities are numerous, because they promise materials with unheard of properties. They promise soft machines where software and hardware are an organic whole. And so that is, the bottom-up approach itself is the one which organically connects the science of the cosmos and planetary science to the science of biology, which was only limited with what we have here on Earth. So what have we learned from the synergy so far? Well, at least two things is the ones that we are learning and that are really amazing. The first one is a basic new understanding of what life is with respect to its planet. Life is essentially a planetary phenomenon. And if we understand even a little bit what biochemistry is, life and the Earth are one and the same thing. The second thing which we understand from this effort so far is that the number of one Earth mass or one Earth diameter, what we are striving as our goal as scientists to detect and discover and study, is not special to planetary science, although it means the world to us. It is a special number for humankind. In the same way in which I think the picture of Apollo showing the Earth rise above the moon means a lot more than the image we all expected to see. Thank you very much.
From Bulgaria.
The more exciting thing about art and science, when we think about this, to me, is that to us scientists, it really matters when we are trying to do something new, enter into a new field. Half of my talk is very difficult to convey and deliver to you, because there is so much baggage in our language which we already use when we talk about life, when we talk about our planet. And what we discover is new. We don't have the proper language for it. And so I'm looking to our friends in the humanities to help us out.
Another thing which came to my mind actually was Gaia, and I recently reread Lynn Margulis, who passed away a few months ago, and Edge reprinted an essay, Gaia is a tough bitch. And this whole Gaia hypothesis says that actually the Earth is more like a living organism than an inert rock. So I was wondering how this whole Gaia idea connects to your idea.
Well, Hans, it's up there, or was up there. Earth and life are one. I would say that these are heroes of the early science, of the interconnectedness of the web of life and understanding it. All that our team is doing is just getting one step further and understanding life and the planet at a slightly deeper level, the level of chemistry and biochemistry. It may appear very trivial to you because, well, to some extent, we all can say that we are all one. But in fact, from a scientific point of view, it's a very much deeper and important statement that planets, and particularly planets like the Earth, are the only place in the universe which can bring together that complex chemistry that then miraculously brings us the richness of life.
And obviously one thing which fascinates me so much, and I think which fascinates many artists, is this whole idea of actually connecting to life beyond the Earth, but also the idea actually for searching for extraterrestrial intelligence. And I was wondering to which extent that sort of connects to the SETI research and how you would evaluate that.
I'm a big supporter of the SETI research. I believe strongly that we should listen, we should look, we should put an effort to do that, and the effort that Jill Tarter and everybody else who is doing SETI searches is amazing, and I support it fully. What I'm trying to do is something which appears less interesting, but is easier to do. It is to detect the existence of microbial life on other planets. Microbes are the king of our planet. They really did something which even we humans haven't been able to do yet. They transformed completely the surface of our planet, including the atmosphere, and in a way in which it can be detected from many light years away. So if we are looking for life, first and foremost, we should try the easiest thing, which is to detect microbes. Then comes the next question: how do we get from microbes to technological intelligence? And that's where SETI comes. I hope they continue to look and listen.
And then there's the question, of course, of data, and data is a big topic for this year's DLD, and you've been actually instrumental in discovering many new planets by also applying new digital technology. And the other day, I visited Thomas Ruf in his studio in Düsseldorf. He's going to actually soon have an exhibition here, big museum exhibition here in Munich. And Thomas Ruf was telling me about his work he does in relation to these extraordinary images which now have very high resolution, which one has using new technology. So I was wondering if you can tell us a little bit about your method, because I think it would be interesting for everybody here to somehow hear about how you find these planets, how you trace them, how you find the data, and what kind of technology you use. And I mean, obviously one thing which in the context of DLD is key: how has the digital technology changed the work of an astronomer?
This is a great question, because people always associate astronomers with a telescope. It's the cartoon version. And yes, we do use telescopes. And yes, if Galileo was alive today, he would recognize the telescopes we use as being telescopes. And people want to see them and say, how is your telescope better? And what's really makes it possible to detect those planets? And half of the answer is yes, the telescopes are bigger. But the other half, and a very important, crucial part, sits right next to the telescope, or on the telescope, or down here on Earth, in a computer room. It's a computer. We cannot possibly do any of those scientific discoveries without being able to analyze the mountains of data that our new telescopes bring down to Earth. We're looking for needles in a haystack, literally, and the only way to get those needles, those Earth-sized planets, is having the power of the computer to analyze the data.
Now, I know we're running out of time, but I've got two last questions, which are very urgent. One thing I wanted to ask you: you've found so many planets, achieved so much. What are your unrealized projects? What are projects which have been too big to be realized? Your dream?
The last time you asked me that question, I said creating a minimal cell. So what do you do once you've done it? Well, then discovering life on another planet. Is that good enough?
Great, yeah. And then Ginevra Erkan is here, and we are working on this book about the future. So I have to ask you, what's the future?
Only astronomers know how to answer a question like that. So of course, our future is cosmic, but also Earth-centric. But not Aristotelian. We are not the center of the universe. It has to be relativistic, as Einstein told us, but we are humans, so it has to be simultaneous. We'll make it, even if the world is not. And finally, as Lisa Randall told us, the future is forever.
It could not be a more wonderful conclusion. Dimitar, thank you so much. Thanks a lot. Wonderful. Thank you so much.